Hello, my name is Alex Weibel. I'm a senior software engineer in AWS cryptography. I've been at Amazon for 7 years, and I've worked on several different teams at AWS. I originally started in AWS working on S3 on Amazon's TLS library S2N. I later moved to Elastic Load Balancing, helping build TLS load balancers. I'm now in AWS cryptography, working on improving the cryptographic algorithms used across AWS. Today, I'm here to talk about what AWS is doing to build post-quantum cryptography for the cloud. So in this talk, I'm going to be covering the following agenda items. To give you a quick summary, I'm going to be giving some background on what post-quantum cryptography is and why AWS thinks it's important. I'm going to be explaining what AWS has done so far in the post-quantum cryptography space. And lastly, I'm going to be showing you a demo of how you can start using post-quantum cryptography today using AWS Key Management Service. So to start off, a lot of you are probably wondering, why do we need post-quantum crypto? There's a few different reasons, but probably the most important one is that the key agreement algorithms that are being used today on the internet will break against an adversary that has a large-scale quantum computer. The problem is we don't know precisely when a large-scale quantum computer will be available. It can take a decade to go from an initial algorithm publication all the way through to a production deployment. And there are years of analysis, implementation, and testing work that need to be done before an algorithm is production ready. And it just takes a lot of time to make sure that we can get things right before we can replace the existing algorithms that are being used today. So here's a list of some of the most common classical algorithms being used today. We have elliptic curve cryptography, finite field Diffie-Hellman, RSA, AES symmetric key encryption, SHA-256, and SHA-3. As you can see, it often takes 10 to 15 years to work 10 to 15 years of work for an algorithm to work its way through from invention to standardization all the way to being widely used. It often takes many years to discover the best known attack against each of these algorithms. And knowing what we know today, a large-scale quantum computer will break the asymmetric algorithms that are being used, like elliptic curve, finite field Diffie-Hellman, and RSA. If we want to be prepared for when a large-scale quantum computer arrives, we need to start building these replacement algorithms now so that they'll be ready 5, 10 to 15 years from now. So here's a timeline of the history of quantum computing. To get a better understanding of where things are going, we can look at where things have gone in the past and how we can give better estimates for where things are going to be going in the future. In the early 80s, the idea of using quantum mechanics to perform quantum computing was conceived. About a decade later, some of the first algorithms started being published where we could actually prove that quantum computers could solve problems not able to be solved efficiently on classical computers. Simon's algorithm solved the hidden subgroup problem exponentially faster than what a classical computer could solve. A few years after that, Shor's algorithm was published, took inspiration from Simon's algorithm, and it can solve integer factorization and the discrete log problem on a large-scale quantum computer exponentially faster than the classical computer. And those problems are the underlying algorithm behind RSA and elliptic curve cryptography and Diffie-Hellman. This means that if a large enough quantum computer could be built, then users could break those algorithms. Grover's algorithm is a search algorithm that can search a list in square root of n time, and it can weaken other algorithms such as AES, but doesn't quite break them. Then, in the late 90s, research and development began to start actually building small-scale quantum computers to prove the properties that the physicists and computer scientists believed they had, to prove that they actually did have those properties. And we've sort of been scaling up to larger and larger quantum computers for the past couple of decades. Last year, in 2019, 50-qubit computers were successfully tested, and we've more or less reached the point where we can no longer simulate quantum computers on classical hardware. The largest quantum computer is able to simulate quantum circuits faster than the largest classical supercomputer. Looking forward a few years, IBM believes that they'll be able to demonstrate a 1,000-bit quantum computer within the next few years. And this brings us to the question that everyone is always interested in. When will RSA be broken? Most people are talking about RSA 2048. This is one of the most commonly used public key encryption algorithms used on the internet today. Sadly, I don't have an answer. Right now, it's estimated that a quantum computer with around 20 million qubits will be able to break RSA. But so far, we've only built quantum computers with about 50 qubits. So we still have a lot of time. But if we expect quantum computers to keep growing at the exponential rate, a little bit like Moore's law, it's likely that they'll be able to reach 20 million qubits sometime in the next few decades. I have a large bubble here, sort of a margin of error of where we sort of expect quantum computers to be able to start breaking some of these algorithms that are actually being used today. But there's lots of varying estimates, and it's hard to be more specific than that. So with quantum computers likely coming sometime in the next few decades, we have to start migrating to quantum-resistant or post-quantum algorithms today. These algorithms run on regular classical computers that we already have access to. They don't need to run on quantum computers, but they use math that's believed to be resistant to some of the algorithms that you can use on quantum computers, such as Shor's and Grover's algorithms. The standardization process for post-quantum algorithms was started in 2016 by the National Institute of Standards and Technology, NIST. NIST has called for submissions for new post-quantum algorithms back in 2016 and has been going through multiple rounds of evaluation, elimination, and improvements since then. And 2 of the algorithms submitted to NIST have Amazon employees as co-authors. And it's likely that this NIST evaluation process is going to be continuing for several more years. Since the NIST standardization process isn't expected to finish for at least a few more years, we're not able to perform a drop-in replacement of the existing classical algorithms that with post-quantum algorithms yet. These new post-quantum algorithms are still being studied and reviewed and might have flaws that we haven't found yet. But these algorithms have still gone through some review. They've still made it through multiple rounds of analysis. And so it's fairly likely that these new post-quantum algorithms being studied will be resistant to quantum computers. Knowing this, it's possible to use both a classical and a post-quantum algorithm and combine them such that we get both the proven security of elliptic curve Diffie-Hellman and the potential quantum safe properties of the new post-quantum algorithms being studied by NIST. So here I have I have an example of how you would use a hybrid key agreement. To give a little bit more context, I've highlighted all of the secrets here in a color. So the orange variables here are secrets that are only known to Alice. The blue variables are secrets that are only known to Bob. And the green variables are shared secrets that are known to both of them. And so to perform a hybrid key agreement, Alice would first generate private and public elliptic curve values, lowercase a and capital A, and then also generate secret key and public key using post-quantum algorithms. Alice would then send both the public values of elliptic curve and post-quantum to Bob. Bob would then generate his own private and public elliptic curve values, and then perform elliptic curve multiplication using his secret and Alice's public value. And he would arrive at the first shared secret between them. Bob would then encapsulate the public value sent to him by Alice and generate a second shared secret and a post-quantum ciphertext. Bob would then send both his public value B and his public post-quantum value ciphertext to Alice, and Alice would be able to generate her shared secret 1 using elliptic curve multiplication and be able to decapsulate the post-quantum ciphertext sent to her from Bob using her own secret key and be able to arrive at the shared secret number 2. Now, both Alice and Bob would have both shared secrets, and they could then combine those secrets using the key derivation function and arrive at the same hybrid secret. This hybrid secret doesn't have a single point of failure. Either elliptic curve Diffie-Hellman could be broken, or the post-quantum algorithm could be broken, and the resulting hybrid key would still be secure. And so it's a combination of both. These hybrid key agreement schemes have gotten the attention of multiple standards organizations, and many have already started work towards documenting them and standardizing them. NIST has started here in the US. ETSI, the European Telecommunication Standards Institute, has started in the EU. And the IETF, the Internet Engineering Task Force, already has drafts available for international use in various protocols such as TLS. Customers do have different data confidentiality requirements. Not all data being secured by customers need to worry about quantum computers coming in a few decades from now. Many systems have temporary SSH keys that are only valid for a few hours, or need to secure earnings reports that will be public in a few months from now. Not every customer needs to worry about post-quantum cryptography or quantum computers. Post-quantum cryptography is most likely to help when users need to keep data confidential for multiple decades. At the same time, post-quantum algorithms haven't been standardized yet, so we can't really do a drop-in replacement. We have to sort of reach for these hybrid algorithms where we can combine the existing security that we know is secure from elliptic curve combined with these new post-quantum algorithms to get the benefits of each one. This allows data to remain confidential so long as either one remains secure. And so why are we investing in post-quantum cryptography today if quantum computers are sort of decades away? Why aren't we waiting for the standardization process to complete in a few years? And I think many users think that if a quantum computer is a few decades away, then I don't need to worry about it. I can just worry about it in a decade or two from now when quantum computers are around the corner. That thinking is not quite correct. There is an attack that users of classical algorithms that are using today are theoretically vulnerable to. If you're sending encrypted data over a public network today, it's theoretically possible for someone on the public network to record your encrypted traffic and send a copy and keep a copy of it well into the future. Then at some point in the future, when quantum computers are available, it'll be possible for that user who kept a copy of it to decrypt that data that they had in the future at that point in time. I'm going to go ahead and walk you through this scenario in a little bit more detail to make sure that it's clear. This scenario applies to any protocol that performs classical asymmetric key agreement, such as TLS, SSH, and IPsec. So we have a client connecting to AWS through the public internet using a protocol that has an asymmetric key agreement. Some user on the public internet that is able to see that encrypted traffic will be able to retain an encrypted copy of it. Keep a copy of it as a sent over the network in real time, and keep a copy of it well into the future. Then, a few decades from now, when quantum computers are available, new capabilities offered by those will be able to be used to decrypt it and get the plain text data. They will be able to run Shor's algorithm on the original key agreement that was recorded in the past and decrypt it in the future. This possibility is concerning if you do want to keep your data secure for multiple decades. So knowing that we want to prepare for a future with quantum computers, the next question is what user interface should we be focusing on to upgrade first? AWS has decided to focus on TLS as our first interface for multiple reasons. It's one of the most widely used interfaces, so any progress we make here will be impactful. It has the most variety of client and server implementations, so it is often the most challenging protocol to work on due to its backwards and forwards compatibility requirements due to the existing large ecosystem of TLS clients. AWS already has the deep expertise in TLS due to building our own TLS library S2N, making the likelihood of success here higher. There's existing standardization efforts for post-quantum TLS that we can also collaborate on with others. Here's an example architecture diagram showing some of the variety of links, interfaces, and protocols that we're thinking about. TLS was one of the first protocols that AWS focused on upgrading and integrating post-quantum algorithms into, but it's likely not the last. AWS is going to be continuing to explore this space and see if it makes sense to add post-quantum algorithms elsewhere. So what has AWS done so far in this space? I'm going to go ahead and give you some of these highlights. Uh, AWS has hosted the ETSI Quantum Safe Cryptography Workshop in November 2019 in Seattle. This is a 2-day workshop with many people working in this field present, and they were able to share their ideas and present their ideas and collaborate with one another. AWS also worked on 2 Internet Engineering Task Force drafts for how to update the TLS handshake to enable hybrid key agreement. These drafts specify the exact wire protocol changes needed to make to the TLS protocol that would allow other TLS implementations to interoperate with S2N. For our TLS 1.3 draft, S2N has interoperability with the Open Quantum Safe project that's built patches into OpenSSL and Boring SSL. And we've also launched Hybrid Post-Quantum TLS into AWS Key Management Service, which is one of our most security-critical services. I'm going to go ahead and dive into some of the work we've done here in more detail. In 2019, we published a IETF draft for how to add an extension to the TLS 1.2 handshake that enables hybrid post-quantum key agreement that's backwards compatible with existing clients. This lets us combine the security of both algorithms so that there's no single point of failure. As long as either key exchange algorithm is secure, the resulting hybrid key exchange will be secure. A lot of this work would not be possible if it weren't for deep integration at the TLS layer. AWS launched our own TLS library, Signal to Noise, back in 2015. It aims to be a safer alternative to libSSL, sub-project within the OpenSSL project, with a significantly reduced and simplified API surface that makes it very hard to do things insecurely. S2N has been written from scratch with a strong emphasis on being small, simple, and secure. We've replaced libSSL with S2N in many places across AWS, including S3, where S2N is currently handling all S3 TLS traffic. In 2019, AWS integrated BIKE and SYKE post-quantum key exchanges into S2N. Both of these algorithms have been submitted to NIST standardization effort, and both have Amazon employees as co-authors. This integration into S2N allows anyone using S2N to start offering hybrid post-quantum TLS cipher suites to others just by changing their cipher preference string. This means it's usually just a one-line configuration change to start enabling these hybrid post-quantum ciphers if you're using S2N. But it's not enough just to add these new algorithms into our own TLS library. In order for customers to use these new post-quantum algorithms, both the customer client side and the AWS server side need to support these algorithms so that it can be negotiated during the TLS handshake. Java is one of the most popular languages used by customers to connect to AWS, so that's the language that we decided to focus on first. Last year, in 2019, we worked closely with several AWS SDK teams to get S2N integrated into the Java SDK using Java's native interface so that users can call into S2N C code from Java. Once this client-side work was completed in the AWS Java SDK, we were able to start work on closing the gap on the server side. In November 2019, we publicly launched support for hybrid post-quantum key exchange in KMS. This feature allows all customers to protect themselves from future store and harbor style attacks that I described earlier. This is especially useful since the data sent to us since the data sent to and from KMS is usually small and security critical. Moving into April of 2020, the second round of the NIST post-quantum standardization effort was coming to a close. NIST had previously announced a request for benchmark and performance data to use for evaluation for which algorithms would move on to the next round. We upgraded both BIKE and SYKE algorithms in S2N from their round 1 version of NIST competition into the round 2 version, and created a sample client and server running in a typical setup on 2 different hosts in EC2. We ran benchmarks for each algorithm and published our performance results in a AWS Security blog post. Later in July, NIST has announced that both BIKE and SYKE did proceed into round 3 of the NIST standardization effort. Our next project in 2020 was integrating a third post-quantum algorithm into S2N named Kyber. Kyber was chosen since it uses different underlying cryptography from both BIKE and SYKE. This gives the post-quantum algorithms implemented in S2N good cryptographic diversity, so that it's unlikely that a flaw in one algorithm would be applicable to another algorithm. Kyber also provides very good bandwidth and performance characteristics out of all the remaining algorithms submitted to NIST. Here's our most recent performance numbers using the latest round 2 versions of Kyber, Bike, and Psych. These are using S2N on C5N 4XL EC2 instances. We set up an S2N client and an S2N server in various AWS regions and measured the 50th percentile TLS 1.2 handshake latency over 2,500 TLS handshakes. No data was sent over the TLS connection. This is just handshake latency. For all the columns, the client remained in US West 2 AWS region, which is in the state of Oregon. And the servers were moving further and further away for each next column. The Psych algorithm used optional assembly optimizations in its implementation on both the client and server side. Moving into September 2020, S2N recently merged in support for using hybrid post-quantum algorithms in TLS 1.3. The TLS 1.3 handshake was a large upgrade from the previous TLS 1.2 protocol that is currently supported and rearranged much of the TLS handshake messages. With TLS 1.3, the number of round trips required to complete a TLS handshake was reduced from 2 round trips to only 1 round trip, resulting in much lower handshake latencies. Merging support for this draft RFC was also the first time S2N was interoperable with another existing hybrid post-quantum implementation. Open Quantum Safe project has implemented this same draft standard in their implementation. Hybrid post-quantum TLS 1.3 was not launched, has not launched yet in any AWS service, but we will be evaluating our options to see if we can change that. One more announcement that was made in September 2020 was the public preview release for the AWS Common Runtime Client. Before this launch, using post-quantum TLS from Java required users to manually download a special developer preview branch of the Common Runtime Client and to build their jar file themselves. With this new launch, customers can now add a regular Maven dependency to their Common Runtime Client, and Maven will automatically download the official preview build artifacts for you. Not every AWS service is supported by the Common Runtime Client yet, but the majority are. So its release is still considered a preview and not considered generally available yet. If you have code that already uses the AWS Java SDK client, here's the sample code that you would need to change in your existing application to start using post-quantum crypto. The first few lines check to see if your platform is using S2N as its TLS library. If S2N supports using the latest hybrid post-quantum TLS cipher preferences, the first few lines check to see if your platform is using S2N as its TLS library, and if S2N supports the latest hybrid post-quantum TLS ciphers. The next couple of lines create the AWS Common Runtime native HTTP client and that knows how to use S2N as its TLS provider. And then the final few lines creates a KMS client that internally uses that Common Runtime client. And then from there, you can use the KMS client however you normally would. Next, I'm going to show you a demo. It's going to be a video of me running a demo application that uploads a key to key management service using hybrid post-quantum TLS. So the first step is we're going to download the demo code from GitHub. Next, we're going to go ahead and change the directory to the demo code directory, and then we're going to use Maven to build that package. And that build is going to be running for a few seconds here. And then eventually, once this build completes, we're going to have a jar file that actually has the demo code in it. And then the final step, we're going to be running this jar file that has the demo code in it. So first, this demo code does that same check. It checks to see if we're using, or if we have post-quantum ciphers available on the platform. And for this demo purposes, we do. And then the next step is we send a request to KMS to create a customer-managed key. And KMS sends back a public wrapping key to the client. Next step is locally we generate a secure AES key and then wrap that AES key using the public RSA key sent to us from KMS. And then the final step is we then call KMS with that wrapped AES key and send that wrapped key to KMS over a TLS connection that is using post-quantum key exchange. And so that key that was imported into KMS would not be vulnerable to this harvest or record and harvest style attacks that I described earlier. And then finally, as the last step of the demo, we just go ahead and schedule that key to be deleted 7 days in the future, just so that we don't leave any unused keys that are not being used. I will also say this demo code that I ran is a slightly modified version of the link below. I modified it slightly just to reduce some of the output so that its output would fit on a single slide here for this demo. This GitHub link in this slide does have other demo code available as well. And now we're all caught up with everything AWS has done so far. Now we're looking into the future. We want to hear from you about what you want us to do next. What AWS services do you think need post-quantum support? What protocols do you want us to add it to next? SSH, VPN, MACsec, we're interested to hear from you. If any of you are interested in this, please reach out. We have my emails here. You can also reach out to AWS customer support, or you can reach out on the AWS KMS forums. And yeah, thank you. Thank you for listening to my talk. If you have any questions, feel free to contact me at the provided email. And I want to give thanks to everyone in the AWS cryptography org and many others in the AWS SDK org. None of these projects would have been possible without the help of many others.